Hey everyone, and welcome right back to The Explainer. Today, we are diving headfirst into the invisible, swirling chaos of sound that's constantly all around us. More importantly, we're exploring the highly objective tools we actually use to capture, measure, and basically tame it. So, if you've ever wondered how audio engineers manage to make a room sound absolutely flawless, or how a simple app on your phone can literally act like thousands of dollars worth of professional acoustic hardware, well, you are in exactly the right place. Grab your notebook, get comfortable, and let's decode the anatomy of sound pressure level, or SPL meters.
Here's our quick roadmap for today's explainer. First up, decoding sound pressure. Then, anatomy of pro meters. Next, anatomy of mobile meters. After that, visualizing the sound spectrum. And finally, the importance of calibration. Let's get right into it.
Section 1. Decoding sound pressure. Okay, before we even look at the meters themselves, we really need to understand the basic physics of how we actually quantify what it is we're hearing. And it all starts with this tiny number, 20 micropascals, or 20 micropascal for short. This incredibly minute number is absolutely crucial because it's the standard reference pressure for sound and air. And why that specific number? Well, it corresponds incredibly closely to the absolute threshold of human hearing, the very edge of what we can perceive. So when you look at an acoustic meter and it says 0 decibels, it doesn't actually mean there is zero pressure in the room. It just means the pressure is exactly equal to this tiny baseline value of 20 micropascals.
And that perfectly brings us to our core definition, sound pressure level, or SPL. You see, if we tried to measure sound pressure using normal linear units, like pascals or pounds per square inch, we'd be dealing with just a dizzying, completely incomprehensible range of gigantic and microscopic numbers. It'd be a nightmare to read. Ratios, on the other hand, are so much more closely related to how our human senses actually operate. The decibel is a logarithmic measure. It takes all those wildly large and small ratios and elegantly compresses them into a highly manageable scale. For everyday audio work, that usually ranges from about 0 up to 140.
But here is the big catch. Human ears simply do not hear all frequencies equally. It's true. At lower volumes, we are notoriously bad at hearing low-frequency bass. So, to compensate, these meters use invisible weighting networks. A weighting, for instance, artificially filters out those lows to match human perception at lower volumes, around 20 to 55 decibels. B weighting is used for intermediate levels, and C weighting is mostly for loud sounds from 85 to 140 decibels, because that's where our ears' response actually naturally flattens out. Oh, and we also have Z weighting. That stands for zero weighting. It's a strict, mathematically flat response from 10 Hz to 20 kHz, completely ignoring human perception to just give you the raw, unfiltered data.
Section 2. Anatomy of pro meters. So how do these physics translate into physical tools? Well, a perfect example of dedicated pro hardware is the Brule & Kjær Type 2236 meter. The physical anatomy here is highly intentional. For instance, notice how the microphone is mounted right at the tip of that tapered body shape? That essentially eliminates distortions of the sound field that would otherwise be caused by the instrument's own casing. It's brilliant. Internally, these pro meters feature independent dual channels. This allows them to calculate both the momentary peak values and the root mean square, or RMS, average values at the exact same time. Add in some built-in octave filters and a real-time clock for logging thousands of data sets, and you've got an incredibly robust, deeply objective tool.
Section 3. Anatomy of mobile meters.
But what if you don't happen to have thousands of dollars to drop on dedicated hardware? Well, thanks to modern digital signal processing, the smartphone right in your pocket can actually serve as highly capable acoustic measurement hardware. Take a look at this. This is the CoolSoft SPL app. It takes the raw microphone input from your phone and translates it using those exact same weighting curves we just talked about. A really cool part of its interface anatomy is the classic analog dial up top showing the current SPL, which is paired with a highly precise digital readout below it. That bottom section is showing you the maximum, minimum, and average decibel levels over a very specific time frame.
Now, a particularly powerful piece of this mobile UI is the relative, or REL, button. Imagine you're tuning a room and you want to see if a brand new sound source is actually louder or quieter than your room's existing baseline. You simply tap REL. It instantly subtracts the averaged baseline value from all future readings. This gives you a clear-cut positive or negative decibel reading, completely empowering you to isolate changes without having to do mental math on the fly. Really handy, right?
Section 4. Visualizing the sound spectrum.
Because sound is rarely just one single static number of overall loudness, modern software actually crams advanced spectral features right into these pocket-sized devices. In-app settings allow users to break the sound down into octaves or even highly detailed third-octave bands. Behind the scenes, the app is running a fast Fourier transform. Now, that might sound intimidating, but it basically means it's sampling over 16,000 data points at 44.1 kHz in just a fraction of a second. At the same time, a time series graph visually plots how the sound pressure level spikes and decays over time. This is exactly the kind of granular data audio engineers need when tracking down some momentary background noise or mapping out a room's reverberation.
Section 5. The importance of calibration. There is, however, one massive catch to using a smartphone instead of dedicated hardware. And it all comes down to how we actually guarantee accuracy. Professional meters use a foolproof physical calibrator. It's literally a device that fits snugly right over the microphone and generates a surgically precise 1 kHz sine wave tone at a strictly known SPL. You simply adjust the meter to match that tone, and you're good to go. Mobile app calibration, on the other hand, is a much more manual process. Because phone microphones vary widely in their sensitivity and overall quality across different models, you have to measure a sound against a known trusted source, like a Pro meter sitting right next to it, and then manually enter that offset data into your app. But honestly, mobile software compensation has become remarkably sophisticated lately. You aren't just limited to a single offset number anymore. You can actually measure up to 3 separate data points across completely different volume levels. The app then works its magic to calculate a linear or even a polynomial curve to fit those exact points. So essentially, it's correcting the physical imperfections of that cheaper smartphone microphone through some seriously advanced software mathematics.
So let's ground all this theory into a real-world application. Say you were setting up a Dolby Atmos game studio. According to Dolby's official guidelines, you would use your newly calibrated meter to adjust pink noise on your main channels to exactly 79 decibels, using a C-weighted, slow response setting. But wait, what about the subwoofer, the LFE channel? Well, if you have a real-time analyzer, you calibrate the low frequencies between 20 and 80 Hz to be exactly 10 decibels higher than your main speakers. But if you only have a standard SPL meter reading band-limited pink noise, you'd aim for just 4 to 6 decibels higher. Hitting these numbers perfectly ensures a mix that translates flawlessly from the mixing studio straight to a consumer's living room.
Let's look at one more typical professional workflow, drawing from Genelic's Smart Active Monitor System. Step 1. You take your measurement microphone and place it exactly at ear height, typically around 1.2 to 1.4 meters, right at the primary listening position. You ensure all monitor distances are perfectly equal. Then, you run your test sweep. And finally, you take the resulting data to adjust your tone controls or digital filters to completely flatten out the acoustic influence of the room. Your SPL meter isn't just spitting out a random number. It's quite literally giving you the roadmap to perfect sound. And just like that, that brings us to the end of our teardown. We've journeyed from the microscopic 20 micropascal threshold of human hearing through those clever, invisible weighting networks, all the way to multi-point software calibration and actual Dolby Atmos room tuning. So now that you understand the anatomy of these incredible tools and exactly how they turn the invisible chaos of sound into perfectly actionable data, the real question is, how will you use an SPL meter to optimize your own listening environment? Thanks so much for joining me on this explainer, and I'll catch you in the next one.